The next video in the Parkour series will be an advanced predictive move/free running system. The player can move towards a movable object and it will calculate which one to move to based on the camera direction. The first type is jumpable objects, which are simple points the player will jump to. For points close to the player, a small jump animation will play. For large gaps, the player will either play a large jump or forward flip animation. For points close and above the current one, a mantle will play. For points further away and above or below the player, a step up or down animation will play respectively. Jumpable objects have an optional spline setting which will make it so the player jumps to the closest position on the spline instead. As shown here, the player is moving to the one being looked at by the camera. If no movable objects are detected, you can hold movement input keys in that direction to exit. The held time threshold can be customized. If there is a floor in that direction, it will play the jump animation then can move as regular. You can also customize whether the player will play an exit animation or if they will just move as normal so you can walk off the point. Next is vaultable objects. The player will vault over designated vaultable objects. It will detect for a land position using advanced calculations. If there is a jump point, the player will land there. You can add as many different vaulting animations as you want. If a floor is detected, it will play a vault over animation. If no landing location is detected, the player will fall after vaulting. The final type is swingable objects. The player will play a swing animation with hand IK to ensure their hands are holding the object. It works with the other objects so the player can go from vaulting to swinging to land on a jump point. The player can also land on regular floors. The system also covers integrating it with other mechanics in the series, which will only be beam walking and ledge climbing. The player can jump to the closest position on a beam which uses the beam actor. After swinging, the player can ledge climb if it was detected. This shows a section of a map using realistic meshes and an environment to show how the system can realistically be used in a game. This is just an example and you can use it however you wish for any map. Here, there is no floor to land so the player exits with a larger fall animation. These are the blueprints for each type, which are all highly modular so you can make any possible object you want, although you must be careful with your level design as it will have limitations in regards to how the player can move. For jumpable object there is a land and peak position which determines the height of the jump and the land position. Vaultable objects has two splines which will be used to determine which side the player starts the vault on based on their facing direction. Finally, swingable objects has positions for each hand's IK location. There is a spline which is used to find the closest position on the object to swing to. First we will get the animations. I will use Mixamo for them. The first one will be forward jump. Make sure to download it without skin. Next search for jump and get this animation. Make sure you don't check in place for any animations that have the option, as we will use root motion to drive the movement. Then get running forward flip. Then search for running jump and get this one. This will be the mantle animation. Next search for jumping and get the following two animations, which will be for step up and step down. Then search for jumping and get the following animations, which will be for vaulting. Get jump over as well. Next get run and swing. Finally, search for jumping down and get this one. You can change up the animations and use any, but it is recommended to use the ones I am until you complete the tutorial so you can ensure everything is working. Next I will use the Mixamo converter to convert them from a Mixamo rig to an Unreal Engine one, since we need root motion which only works with the standard Unreal skeleton setup. For all the animations, press custom root motion and set frame, height, and rotation to 0. This is being done since we need the root bone to move in the Z-axis as well, since motion warping will modify it. If we convert it by default, the root bone stays at 0 in the Z-axis. I will put a link to the software in the description. Then open Unreal Engine. I will make a new folder called Predictive Move. Make a new folder for the animations and import them all. Select all, right-click and choose Edit Selection in Property Matrix. Search for root motion and enable it. This enables it for all the animations, which is much quicker than manually setting it for all. Open one of the animations and select the root bone. Uncheck root motion and check if it is moving in the Z-axis. For some reason, despite setting frame, height, and rotation to 0, it doesn't work the first time. I found the fix for this is to delete the output animations, repeat the steps with setting frame, height, and rotation to 0, then re-importing. Now the root bone is moving up as well. You can drag and drop the same animations to re-import and overwrite all of them easily. Since there are many animations, I will make subfolders for each type and also rename some to be more fitting. I will speed this part up so you can pause if you want to rename them exactly as I am. Open the jump folder and make anim montages of all of them. Open the big jump one. I will change the rate scale to 0.75 as this one was too fast. Right-click in Notifies and add a motion warping notify state. If you don't have this, then enable the motion warp plugin first. The start point is the animation start and the end should be the point at which the jump is at the highest point. It is recommended to set the start and end times to a similar time that I show, as it has been tested to ensure it works accurately in game. Set the warp target name to peak pause and uncheck ignore Z-axis. I will change the mode to exponential out to make the jump look more natural, but you can use any curve you want for it. Add another notify that starts just after the previous one ends. The name will be land pause and again uncheck ignore Z-axis. Set the end time of the montage to 0.6 by clicking on the animation name in the slot. Then go to the point where the player just lands. Add a new notify track. Add a montage notify called jump end. The purpose of this and all used notifies will be explained during the coding. Copy all 3 notifies. Now open the mantle jump one. For this animation, set the start time to 0.4 and end time to 1.4. Add a second notify track and paste the notifies. Adjust the times of them as shown. You can hold shift and drag the notify to move both that notify and the time. Next will be running forward flip. Set the rate scale of it to 0.9 as this one was a bit too fast too. Change the start time to 0.2. Add the second notify track and paste and adjust the notifies. Next will be small jump. Increase the rate scale to 1.5 as this one was too slow. The start time is 0.2 and end time is 1.8. Repeat the notify process. Then open step down and change the rate scale to 1.5 as well. Change the end time to 2.1 and repeat the notify process. so they are easy to understand for the programmer. It will have 3 values called Jumpable, Vaultable, and Swingable. Next, make a blueprint interface called Movable Object. Blueprint interfaces are a good programming practice which allows for different blueprints to implement the same function while running different code. This will allow for different movable object types such as Jumpable and Vaultable to share a common function, but that function does different things for each actor. The first function will be called getType, which will have an output called type with the variable type being the object type enum we made. I will put it into a category called general. Make a new function called getPeakPosition. It should have a vector output called location. Make an identical function called get change via construction script, and it won't be the most efficient method as well. I will quickly duplicate one of the prototype meshes to use as the default mesh. The mesh is now showing in the viewport with the correct material. I will also change the default value of landpass so it matches up for this mesh. Now open the Get Land Position function under the Interfaces section. By default it will return the land position's world location. This function will be overridden for the different types where needed. Next, make a function called Find Face Direction. It will have two scene component inputs called front arrow and back arrow. It will have one float input called min dot. Add a Boolean output called facing. Add a scene component output called facing arrow. Then add a Boolean output called is front arrow. This function will be used to determine if, and which side of the object the player is facing, returning the corresponding arrow component. Drag out of the front arrow and get the forward vector. Then get the dot product. Next get the player character's actor location and find the look at rotation between it and the actor location. Get the forward vector and connect it to the dot product. This returns a value between 0 and 1 of how directly the player is facing the front arrow. Duplicate the forward vector and dot product for the back arrow. Get float greater than the min dot for both. Connect them using an OR operator. This checks if the player is facing either of them to an extent, which is determined by the min dot input. Set this as the facing output. For the facing arrow, get a select node. The index will be the first greater than. Make sure you drag into the inputs and not the node, as that will make a new input as I did for the back arrow. I also set the variable type of facing arrow to movie scene component instead of scene component accidentally, so we'll fix that. If false, it will be back arrow, and if true, front arrow. The is front arrow output will be the first greater than. I will now comment the function. Make a child blueprint of movable object called Jumpable object. Add a scene component called Jump Peak Height and a spline component. These are unique to jumpable objects, so were not added in the master blueprint. Set the spline's Z location to be on the surface of the mesh. Then go to the construction script and set the relative location of jump peak height to a variable called peak height pos, like we did for the land position in movable object. This time, split the pins and only set the Z location. Then set peak height pos, splitting the pin and leaving X and Y to 0 with Z being connected. This is since we only need the Z location data from it. Add a branch and promote the condition to a variable called useSpline. Enable instance editable and set the default value to false. If false, destroy the spline component. Then open the getType function. The type is already at Jumpable, but for the other ones we will change it to their respective ones. Next, in peak position get the spline and check is valid. If valid, connect it to the return node. Get the spline and find location closest to world location. Change the coordinate space to world. The location should be the player character's actor location. Make an array using the return value, adding a pin and connecting the player character's location to it. Then get vector array average and split the pin. Split the return node's output as well. Connect only X and Y. For Z, get the Z location of jump peak height. If not valid, get actor array average location. Make an array with self and the player character. Add a return node and set X and Y to the average with Z being the same as the previous one. This code finds the peak height position using the set Z height and the XY locations being the average between the player and either the actor or the closest position on the spline based on if using spline. Next open get land position. Copy the shown nodes, which are very similar to what we just did for the peak position, but we are returning the whole value with all three axes. Finally, open the getSpline function. It will return the spline. I will quickly showcase this blueprint. Make sure to set instance editable and show 3D widget to true for peak height pos. I will give it a default value of 0, 0, 200, so the Z difference between this and the land position is 100. Go to the moveable object and make sure you set the 3 mesh variables to instance editable as well. Now we can easily change the mesh and the material also changed as well. The rotation can be changed easily. Since this is a longer object, it is better to use spline. Checking the box will make the spline show up and it can be adjusted to fit the object. Make another child blueprint for vaultable objects. I will make a quick cube mesh for the default one and change the mesh scale to make it wider. Add an arrow component called front arrow with the rotation being 90. Duplicate it for the back arrow and change the rotation to -90. Next add a spline called front spline. Adjust the position so it goes across the width and just at the edge. Make sure you put it in the edge where front arrow is. Duplicate it for the back spline and adjust the position accordingly. Open Get Type and change the type to Vaultable. Now make a new function called Get Vault Direction and Locations. It will have two float inputs called min dot and z offset. It will have one Boolean output called canvault. Add two vector outputs called start location and end location. Then add a rotation output called direction rotation. This function will return if the player can vault by checking if they are facing either side and the transforms for vaulting. Get front arrow and back arrow. Set these as inputs for the find face direction input. Make sure to set that function to pure. Min dot will be the min dot input of this function. Set the facing output as the canvault output for this one. Find location closest to world location and set the target to a select node. The index should be is front arrow output of find face direction. If false, set it to front spline, and if true, then back spline. Set the world location to the player character's actor location and change the coordinate space to world. Subtract a vector from it, splitting the pin and setting z to the z offset input. Set this as the start location output. Duplicate this part and invert the select node values. Set this as the end location. Get the forward vector of the facing arrow and make rot from X for the direction rotation. This returns the front-facing rotation of the target direction. Make one final child blueprint for swingable objects. I will change the mesh to a cylinder where the center is the pivot and adjust the scale and rotation so it is like a bar. Add a scene component called hand IK root. Add two scene components as a child to this called left hand and right hand IK position. Then add a spline and adjust it to fit the bar. Don't extend it all the way to the end, as since if the very end is detected the player won't have space for one of the hands IK, so offset them at each end a bit. Add a front and back arrow to this as well, setting the rotations accordingly. Set the left hand IK position's relative location to a variable called left hand IK pos in the construction script. Set instance editable and show 3D widget to true. I will set the default X value to -30. Duplicate it for the right hand IK and replace the variable and default values X to 30. Then get land position and destroy component as we don't need it for this one. Open get type and set the type to swingable. Next open get land position. Copy the shown nodes. Set this as the hand IK root's world location. This will move the parent scene component while keeping the relative hand IK positions the same so the player can swing at any point in the spline. The find location closest to world location return value should be the return node's output. Now make a new function called getSwingDirection and IK. It will have one float input called min dot. It will have a Boolean output called canSwing. Add two vector outputs for left and right hand IK. Then add a rotation output for the direction rotation. Copy the nodes shown which are similar to the calculations done for the Vaultable object. To correct the animation and ensure the player is holding around the bar and not into it, we are adding this offset value using the forward vector of the direction we are moving. Negating the vector before multiplying moves the hand to the opposite direction, as this is what we need. I will now quickly run through the 3 blueprints. When you drag a jumpable object into the level, you can easily change the peak height and land positions. This enables for free level design. The swingable object's hand IK positions can easily be changed, so differently shaped bars and bars of varying lengths will all work for this, although the spline must be modified to match the mesh. Vaultable objects have the 2 splines that can be modified to match any object, as well as a land position that can be changed. That will be all for this part. In the next one, we will start with the character blueprint. You can purchase this project using the link in the description if you want. If you enjoyed, like and subscribe for more content. Thanks for watching.